Okay, so today we're going to go ahead and talk about impulse, and we'll talk about both the calculus version of impulse and regular old impulse when we're dealing with a constant force. Okay, so what I want you to think about is think about what impulse means. Okay, so when I think of impulse, I think of like a sudden, impulsive, like urge or like desire to do something. So we all have like impulses in our everyday life. Let's go ahead and now think about a physics definition for impulse. So oftentimes it's like a big thing, like you're like, oh, I'm going to do this, boom, and it's over like a short time period. So what an impulse is in physics is it's typically a large force that is exerted over a short time period. So it's a huge force that is exerted over a short time period. So I think of it's like maybe I want to throw a ball. So I exert a force on that ball over a pretty short time period, and I exert an impulse on that ball. I'm sure you all could think of a zillion impulses in your everyday life. Okay, so now I would encourage you, guess an equation for impulse and then check back in on the video. Okay, so the symbol we use for impulse is J. So J is impulse, and that is going to be, it's a large force. So F is force exerted over. So per means divided by, but over means like over that time. So we're going to multiply that times change in time. So this is, and I'll put this here, this is change in time. And this is our equation for impulse if the force is constant. So this is true if the force is constant. Okay, so now let's go ahead and think about what are the impulse units for impulse. So let's just look at this equation. The units are, we're multiplying force times time. So units are just going to be newtons times the change in time units, which are seconds. And we got our units. Awesome. Yeah, so now we're going to go ahead and talk about another example involving impulse. So let's say you apply a force, a constant force of 300 newtons for 0.2 seconds to a box at rest. Okay, so again, this is a short time interval, which technically an impulse could be any time interval, but it's typically a short time interval. So what might this impulse cause the box to physically do? Okay, well, it could accelerate. So its velocity will change, so it'll change its velocity, and that'll also mean it'll change its momentum. Cool. So all those things would totally happen to this box, or could happen to this box. So let's go ahead and calculate the impulse. So the impulse J is going to be force times change in time. So the force is 300, change in time is 0.2. So 300 times 0.2 is, sorry about that, is 60. And then again, the units are newtons times seconds. We're multiplying those two. Cool. So let's go ahead and create a force versus time graph that represents this situation. Okay, so time is on the x and force is on the y. Okay, so force is 300 newtons. Let's think about it. Is it always 300 newtons or sometimes 300 newtons? It is always 300 newtons, so that is just a straight line across for 0.2 seconds. Okay, so now how can you find impulse from a force versus time graph? So I encourage you to pause this video, think about it yourself, and then check back in. Okay, so if I look at this itself, I need to get to 60 somehow. So a good way to do this is I can calculate the area. So the area under the curve of a force versus time graph is impulse. Cool. So let's think about this. So because we multiplied, because this is essentially 300 newtons, this right here is 0.2 seconds. So to find the area, we're just multiplying. So we're just multiplying 300 newtons times 0.2 seconds, which is 60 Newton seconds. Cool. So we're finding the area. So let's go ahead and add a little more calculus ideas. So the area under the curve we know is the integral. Again, integral is just a fancy name for area under the curve. So with the integral of force versus time graph, is impulse. So let's go ahead and write an equation involving this. Again, I encourage you to try it yourself and then check back in. Okay, so impulse we know is going to be the integral of, so again, the integral symbol, which means the area, of a force, and the force will be some function of time, first time graph, so it's the force function with respect to time. So we're integrating over time dt. So this is going to work. So this will work for all situations, and it'll be especially good to use it if the force is not constant. Cool. So one thing I like to think about is like, what is this equation similar to? So this equation is going to be similar to the work equation, which is the integral of force with respect to distance. So with work, we're integrating with respect to position, while impulse we're integrating with respect to time. So a couple subtle differences. Okay, so let's go ahead and try one practice problem involving impulse. Okay, so we're going to go ahead and solve one problem together. So we have some force on a 2 kilogram mass described by this function. Okay, so we want to find the impulse. So this force is not constant, so we're going to have to use those calculus ideas. We haven't quite covered integrating yet, just graphically. So let's go ahead and do it drawing a graph. Okay, so we have our force on the y-axis and time on the x. Let's go ahead and draw this. So it's 6 is going to be the y-intercept, and it's from 0 to what, 5 seconds? So when it's at 5 seconds, it's going to be at 16. If I plug in, yeah, f of 5 is going to be 2 times 5 plus 6. So yeah, 16 newtons. Cool. That starts here, and that is a constant line. Okay, so again, we know impulse is going to be the area under the curve of a force first time graph. So it is going to be this whole entire area. Cool. So let's go ahead and look at this. So we want to find the impulse, so that's the area under the curve. We could do a little trapezoid formula, but I find that tricky, and I just like to split it into shapes I know. So this bottom shape, that is 6 newtons by 5 seconds, so the area equals 6 newtons times 5 seconds, which is 30 newton seconds. This top one, let's see, this is 10 newtons by 5 seconds on the bottom. So the area, this is a triangle, what, 1/2 base times height. So 1/2 the base is 5 seconds. The height is 10 newtons. So let's see, this is going to be 25 newton seconds. Cool. And then the total area equals what? 55 newton seconds. Cool. So that's going to be the impulse acting on that 2 kilogram mass. And again, that impulse will cause the mass to accelerate, change its velocity, change its momentum, all that good stuff. So let's go ahead and try to do this algebraically as well. And some of you have probably covered this before, and some of you might not, depending on what type of the area you're at. So impulse we know is the integral of force with respect to time. So the force function is 2t plus 6, and we're integrating with respect to time. We already have our limits of integration, so t equals 0 to 6. Or, so, excuse me, not 6, 5. Let's get that right. Okay. So now let's just go ahead and integrate. So integral of 2t is just going to be 2 squared. Integral of 6 is going to be 6t, and we're integrating from t equals 0 to 5. So let's see, t squared, so let's plug everything in. So it's going to be 5 squared plus 6 times 5. Take away the other limits, which is what? 0 squared plus 6 times 0. Cool, so 5 squared plus 6 times 5 is 55. Last term turns out to be 0. We are left with 55 newton seconds. So cool. So we got the same thing both ways. That's awesome. So keep in mind we were using those ideas of calculus because this force is not constant. Awesome. Thanks for watching.